Okay guys, how's it going? This is going to be the first video with half-lives and integrated rate laws, first order and second order reactions. What do these mean and how do we solve problems around them? So let's look at this problem. The thermal decomposition of N2O5 to form NO2 and O2 is a first order reaction. So let's highlight that bit, that's really important. The rate constant for this reaction is some number, 5.1 times 10 to the negative 4, and we're given the temperature, 318 Kelvin. Calculate the half-life of this reaction. So let's go through this how I would see it. I see first order reaction, and the first thing I think is, well, what is the first order integrated rate law? And in another video, I may go over the derivations for these, but it does require a fair amount of calculus, which is why I'm a little hesitant to do so. But what you can do is just get some flashcards out, or just using it enough, you will remember the integrated rate laws. So if you haven't done so, the integrated rate law for a first order reaction is the natural log of A at time t is equal to the negative kt, which is our rate constant, times time, not temperature, plus the natural log of A at time 0, so the initial concentration. So yeah, to break that down a little bit more, this guy right here represents my initial concentration. And what I mean, my concentration of A at time t, that's just any time you want to be. You want the t to be. Any time you want. So in this case, we're calculating the half-life. So it would make sense then that the time that I want it to be would be the half-life time. So that's what we're going to be utilizing when we're solving this equation. So to the right here, I'm going to put what the half-life equation is for a first order rate law. And you could simply memorize that. But what I'm going to do in this video is show how you could potentially solve it for yourself. And I think that's ultimately the helpful, the helpful element of this video is that I can show you how to derive the half-life equations if you forget them. So that limits the amount of things you need to know, and instead it'll bolster your algebra and everything. So and your understanding of the equations as a whole. So the half-life for a first order integrated rate law is 0.693 over k equals my time for my half-life. And just for clarification, 0.693 is the natural log of 2. And that'll be a little helpful later, because you'll see that when we get done deriving this, you will be surprised to see that we could do this ourselves. We can do this with this integrated rate law. So let's solve. So let's take a look. So the integrated rate law is given to us, and what we can do first is we want to solve for t. And that's going to be helpful if we first subtract the natural log of a over to the other side. And if we do that, we get the natural log of a at time t, the natural log of a naught is equal to negative kt. Well, because we have two natural logs subtracted with the same base, we can make this into division instead using the natural log rules. So, like for example, the natural log of x minus the natural log of y, well, that's just equal to the natural log of x over y. So I'm going to be utilizing that in this particular problem. So, okay, so natural log of a minus that, well, that must be then the natural log of a at time t. Let me give myself a little more space, it's kind of ugly. The natural log of a at time t, number a, initial. And that's just using that rule that I said earlier. Okay, that's equal to minus kt. Okay, so remember that the brackets represent concentrations. So my initial concentration is going to be just A naught, but my concentration at the half-life will be, well, half of what I started with. So I can rewrite this as the natural log, instead of having A at time t, my concentration there, I'm just going to write it as half the concentration of what I started with. So it's going to be 1/2 A naught. because that's what it means to be at the half-life. My concentration is half of what it is when I started. So my this thing still stays here, A naught. But notice in my division right here, these both will cancel. So what I'm left with is just the natural log of 1 over 2. So then let's fix that. Let me give myself some space. So then I have the natural log of 1 over 2 equals negative kt. Okay, so using that rule we said before, since the natural log of x over y, I can write a subtraction. Let's do that here. So that's going to be the natural log of 1 minus the natural log of 2 equals negative kt. Well, what is the natural log of 1? Well, the value of natural log of 1 is equal to 0. So what I'm left with is just minus ln of 2 is equal to minus kt. The negatives will cancel, and I'm left, if I divide the k over to the other side, I get the equation I was talking about in the beginning, which is the natural log of 2 over k equals my time at my half-life. Now, this little time at half-life, you'll see that represented in the textbook as t1/2. That's just a subscript telling you that it's the half-life time, the time it takes for you to reach half the concentration of your initial starting amount. So I wanted to show you this because I think it's useful in understanding where these equations come from. At least in my studies, when I took this class, I took it seriously to understand where the equations come from, because otherwise I'm just memorizing equations that I will never remember for further use. But if you know how to derive it yourself, you can use this in anything. If you ever happen to be using kinetics, if you're a chemistry major, I absolutely recommend you memorize these. So we can actually do the problem now by plugging in our values. So let's take a look. So the thermal decomposition is a first order, and this is the half-life for a first order reaction. The rate constant is given to us at 5.1 times 10 to the negative 4, and that's literally all I need to plug in. Notice that there's no need to use this Kelvin. That is a trap. We don't need it. We need, because our rate constant already takes into account that temperature. So don't worry about it. The T in this equation is referring to the time. So remember, kinetics is all about time. So we can determine the rates of reactions, and the speed at how long it will take. So let's figure this out. So it's going to be just plugging our values in. It's going to be the natural log of 2 over my k constant, which is given to us, which is that 5.1 times 10 to the negative 4. And I'm given my time. All right, so it's just going to be the natural log of 2 over that number. And notice that, like, dimensionally, our units will be pretty good, because this second has a -1. We can raise it over to the numerator, and my answer will be in seconds, which is what we want for our half-life time. So it's going to be the natural log of 2 over 5.1 times 10 to the negative 4. My answer, T of 1/2 is equal to 359 seconds. There we are. So again, if you had your cheat sheet with you, this is a really easy problem, because you quite literally need to use just the equation that you have right here, that the time for the half-life is equal to the natural log of 2 over k. And yeah, this would be an easy problem if you were given that. But the value in deriving these equations is very useful, and I think it really actually helps you what's involved in this equation, and it'll prevent you from misusing this equation on your cheat sheet. So I hope this was a helpful video. We'll go over a couple more problems in the future. So I hope this was helpful, and I hope to see you next time.